Hey, welcome back. Now we're working with linear models in 3.1. We've kind of already seen a lot of these models in 1.3, but we might not necessarily have had the ability to solve them. Now that we have the ability to solve them, we're going to kind of revisit them and solve them. So here we go, 3.1 linear models. And we're going to begin with the growth and decay formulas. And we'll look at radioactive decay and I guess growth with regards to bacteria. The radioactive decay we can use for carbon dating, so that's something that people are kind of like somewhat familiar with from popular culture. But anyways, let's look at growth and decay. So the formulas for growth and decay are just the exponential growth formulas. Well, that's what will result when you solve these differential equations, right? So the rate of change of the population is proportional to the population. And then we'll probably have some sort of initial value, the amount of the population at time t sub 0 will equal some value we'll call x sub 0. Okay. These problems could get a little annoying in the way that they're kind of set up. Let's look at, I guess, example 1. Look at example 1. The culture initially has p sub 0 bacteria. So when t is equal to 0, p, the population, so maybe we should just put 0 in there for t. The population at time 0 will be p sub 0. Okay. Then it goes on and says at t equals 1 hour, so when p of 1, the number of bacteria will be 3/2 of the initial population. If the rate of growth is proportional to the number of bacteria, so that's just saying that the dp over dt is proportional to p. Determine the time necessary for the number of bacteria to triple. Okay, so we want to kind of figure out what it has to be in order for us to have 3 times the original population. Okay, so if you want to, you can just skip to the chase, go to the chase, or whatever they say, and solve this differential equation. We solved it by separation of variables before, but you can actually solve it using integrating factors, and I think that's what the book does. We're going to move the kp to the other side, set it equal to 0, and then go mu equals e to the negative k, and of course you have to integrate this with respect to t, so it would be e to the negative kt. So you multiply that equation by that factor, and then you collapse it, so it'll end up being the derivative with respect to t of p times e to the negative kt. On the other side, you just have 0 times e to the negative kt, but it's just 0. And then we can integrate both sides with respect to t. On the left, the integral and the derivative cancel each other out. You have p e to the negative kt. On the right side, the integral of 0 is just c. Okay. And then you could multiply both sides by e to the positive kt, and you get what you would have gotten if you did separation of variables anyways. So you'd end up with p equals c e to the kt. Okay, great. So now we kind of go back here to the top. Here's my formula as it sits. And I use these initial conditions in order to solve out for the unknown parts, right? So I'll begin with this p of 0 is p sub 0. And so I have p sub 0 equals c e to the 0, right? That means that c is just going to be p sub 0. So I can rewrite my equation now as p equals, I substitute in p sub 0 for c, and then have e to the kt. Okay? So that's my first step. Now I go back up to the top and look at the second initial condition. This is going to allow me to solve for k. All right? All right, so I'm going to plop that into this equation. P of 1 equals 3/2 p sub 0. And so I'm plugging in 1 for t. So I have e to the k times 1, which is just k. And then I could solve for e to the k by dividing both sides by p sub 0. And I'll have e to the k as 3/2. Then do ln on both sides. So I'll have k equals ln of 3/2. Okay. Okay, so now my formula, putting all this together, is p equals p sub 0 e to the t ln of 3/2. And I should be able to use this in order to figure out when the population will triple. Okay. Okay, so let's try that. I want to know, I'm solving for t this time. So when is the population going to be triple the initial population? So 3p sub 0 equals p sub 0 e to the t times ln of 3/2. I want to solve for t. So divide both sides by p sub 0. You get 3 equals e to the t to ln of 3/2. And then I could take ln on both sides. So I get ln of 3 equals t ln of 3/2. Then solve for t. So t will equal ln of 3 divided by ln of 3/2, whatever the heck that is, right? So you just go to your calculator. And I can find mine. So 1 second. Find my calculator. So what do I have? Second ln of 3 divided by second ln of 3/2 is 2.7095. And the time unit hours for this, for the number of, it'll take about 3 hours for the number of bacteria to triple. Okay, let's make sure that's what they got. Yeah, 2.71 approximately. Okay, great. They note here that if you have a k value that's negative, you'll have growth, or sorry, decay. So for decay, the k value is less than 0. For growth, the k value is greater than 0. Okay. So then this problem, example 1, was an example of growth, population growth. From there, they're going to go into radioactive decay and start talking about half-life. That is when the k value is negative. Okay, so moving into half-life, and also we'll look at, I guess, carbon dating is in there. So carbon dating and half-life. Okay, so let's look at this first guy. We're talking about plutonium. A breeder reactor converts relatively stable uranium into the isotope plutonium-239. After 15 years, it's determined that 0.043% of the initial amount of the plutonium has disintegrated. Find the half-life of the isotope if the rate of disintegration is proportional to the amount remaining. Okay, so they give you some information. When T is equal to 15, the amount of plutonium, it's 0.43 has disintegrated. Okay, so not much of it is gone. In other words, 1 minus 0 point, and that's given as a percent, so you really have to move the decimal 2 places to the right. So you would end up with 0. Or maybe to the left rather, right? So 0.00 and then 0.43 times a sub 0, the initial amount. Okay. So if you just put in 0.00043 times a sub 0, that would mean that very little of it is left. But what they're saying is only 0.043% of it has disintegrated, right? So there's still a lot of it left. So 99% of it is left. And if you subtract 1 minus the point, that's what you get, like 99%, right? So let me subtract that real quick. It's 0.00043 is 0.99957 a sub 0. Okay, great. They tell us in the information above, I think they give you the half-life of plutonium 239 somewhere. There's isotope 238. I'm not seeing it. Maybe they put it in a chart. Sometimes they'll put it in a chart. Ah, what the heck is it? There's radon. There it is. 4.5 billion years. Are you kidding me? Oh, that's for lead. Sorry. So I don't think it's giving it for the half-life here. Does it give you a half-life? I don't think it does. Let's see if we can figure out just with what we're given. Okay. So again, our formula is, long story short, we don't need to go through and solve the differential equation. It's just going to be A equals A sub 0 e to the kt. Okay. I think we use that initial condition to solve for the k value. So when t is equal to 15, so we have 15k, the output there, whoops, hold on, let me, hello? Oops, somebody dropped by and said hello. Am I recording still? Yeah, okay. So we should be able to solve this, right? In this case, 0.99957 a sub 0, divide both sides by a sub 0, 0.99957 equals e to the 15k. Take ln on both sides, and you get 15k equals ln of 0.99957. Divide both sides by 15, so k will equal ln of 0.99957 all over 15. And then we should be able to use that expression to answer any questions they throw our way. So what do they want to know? They want to know, find the half-life. Okay. So to find the half-life, we can go back to the, we don't even really need the initial amount. Let's rewrite our equation using the constant k now. So we have t times ln of that 0.99957 all over 15. And then we can set it so it's equal to the half the initial amount, and that will allow us to solve for t for the half-life. Okay, so e to the t ln of 0.99957 all over 15. Divide both sides by a sub 0, so get 1/2 equals e to the t ln of 0.99957 all over 15. Take the ln on both sides, and we get t ln of 0. Annoying number. 15 equals ln of 1/2, and then multiply by reciprocals, and t will be 15 ln 1/2 all over ln of 0.99957, and then we can get a nice approximation there. Just a little Wolframize it. And see what happens here. So 15 ln of 1/2 divided by ln of 0.99957, and it looks like a pretty long time, 24,174 years about. 74 years. Let's see what the book says. Oh, they rounded differently than I did, apparently. they got an approximation for K, so my number is better probably because I didn't use an approximation. Okay. So anyways, carbon dating, you can use the half-life of carbon-14. Apparently, once an animal or something like that dies, the it's going to stop absorbing carbon-14. It'll start to decay. So if you know enough information, you could determine how long that object has been deceased. Let's look at example 3. Everybody apparently knows the half-life of carbon-14, and this example is 5730, 5,370 years. We're saying today the commonly accepted value for the half-life of carbon-14 is close to 5,730 years. Okay, so the half-life, 5,730 years. They're saying a fossilized bone is found to contain 1% of its original amount of carbon-14. So when it dies, that carbon-14 in its body starts decaying. And you can tell how long it's been alive by how much of the carbon-14 is left. Okay, so the formula we're using again is A equals A sub 0 e to the kt. So C, I mean, they tell you basically the amount left over at time 0 is A sub 0. Then if you plug 0 into that formula, so usually the formula I'm having you memorize is A equals C e to the kt, but you're always going to be able to put this in for C. Okay, so we just plot that initial value. We don't know what it is, but we're going to put it in there. Okay, and then we have e to the kt, right? Well, I mean, okay. So there's our formula. Here's our formula. Right. So I could use the half-life to figure out the k value. So 1/2 of the original amount will be left when t is equal to 5730. So you just plug 5730 in for t, and then solve for k. So I'm going to divide both sides by a sub 0. You have 1/2 equals e to the 5730k, and then take ln on both sides. You get 5730k equals ln of 1/2. Divide both sides by 5730. ln of 1/2 divided by 5730. I don't like to get approximations, so I'm not even going to approximate that. I'll plug it back into my formula for k. So now officially my formula is A equals A sub 0 e to the t ln of 1/2 all over 5730. The problem is saying that 0.1% of the original amount is the original amount of carbon-14 is left. So what you do is say, all right, A sub 0 e to the t ln of 1/2 all over 5730 equals currently 0.1 of the original amount. So you just set it up like that. Divide by A sub 0, and then you could solve for t. So you get 0.1 equals e to the, and it should be 0.01. I apologize. I have to convert that. Moving the decimal 2 places to the left, I guess I get 0.001. Okay, so dividing both sides by A sub 0, you get 0.001. E on the other side, e to the t ln of 1/2 all over 5730. Take natural logs on both sides, and you get t ln of 1/2 all over 5730 equals ln of 0.001. multiply by reciprocal. So I get 5730 ln of 0.001 all over ln of 1/2. Okay. Wolframize it. And it should give you the answer. Whoops, I put in too many fraction bars there. Didn't like that. So it looks like the object is 57,000 years old. 57104 years to the nearest year. Let's see what their approximation is. About the same. Okay, great. So then they're talking about the carbon-14 in further detail if you're interested. They used it in the shot of Turin, apparently. Okay, so the next type of application is from Newton's law of cooling and warming. So Newton's law of cooling, warming. And the model we had from the section 1.3 was that the rate of change of the temperature is proportional to the difference between the temperature of the object and the temperature of the surrounding material. Okay. Again, you could solve this via your integrating factor. I think they just did separation of equations in the example. Let's do an integrating factor and see if we can get the answer that way. They're giving you some initial conditions here. So example 4, when the cake is removed from an oven, its temperature is 300 degrees. So that's basically T of 0. Okay? So that would be 300. 3 minutes later, so T of 3 is going to be 200. And then they want to know how long it takes until, how long will it take to cool off to a room temperature of 70 degrees. So the surrounding medium temperature, T sub m, they're going to say is the 70 degrees in the room. Let's see if we can go ahead then and use this information to solve. And we'll use integrating factors. So dt over little dt is k times t minus 70. Okay, so we can distribute the k. dt over dt is k big T minus 70k. And then I can move this term to the other side. So I got dt over little dt minus k big T equals negative 70k. My integrating factor will be e to the integral of negative k dt, which will be e to the negative kt. Multiply through, collapse the left-hand side, get the derivative with respect to t of mu, e to the negative kt times t. On the other side, you have negative 70k e to the negative kt. And then we can integrate both sides. Over here, the integral and the derivative cancel. On the right-hand side, doing a u sub for negative kt, we would end up with du being negative k dt. And so dt would be negative du over k. So there would be that factor of negative 1 over k, and so you would have negative 70k that you could factor out, but then there would be a factor of negative 1 over k. And then you have just the integral of e to the u du kind of left. And then you integrate that, so e to the negative kt times t equals, the k's cancel, negative is positive, and the integral of e to the u is just e to the u, but back subbing you get e to the negative kt. Add on a c, divide everything by e to the negative kt, or if you'd rather multiply everything by e to the positive kt. And then you get 70 plus c e to the kt as your model. Let's see if that's what they got. Yeah, same thing. Okay, now we're going to use the initial values to solve out for the constants. There's a c and a k there. So again, remind myself, T of 0 is 300, and then T of, what did they say, 3 is 200. Okay, so the T of 0 first, so 300 equals 70 plus CE to the 0. So I would get 230 equals C when I subtract the 70 over. So my equation now becomes T equals 70 plus 230 e to the kt. Now I want to solve for k, so I can use the other initial value there to the left. The T of 3 is 200. 230 e to the 3k. I want to solve for k. Move the 70 over, so you should get 130 equals 230 e to the 3k. Divide by 230, you get 13 over 23 equals e to the 3k. Take ln on both sides, and you get ln of 13 over 23 equals 3k. Divide both sides by 3. ln of 13 over 23 divided by 3. And I'm going to leave it as that, not get an approximation. Okay, so T will equal 70 plus 230 e to the T ln of 13 all over 23 all over 3. Okay, so what do I need to do now? I need to find how long will it take to cool off to 70 degrees. Okay, so I'm going to put 70 in for the temperature and solve for T. Okay, so move the 70 over. That would be 0. Divide both sides by 230. That's still 0. Okay, so I made a mistake somewhere. Yeah, so you're not going to be able to solve this. That's weird. Okay, so they go on to say that the limit, yeah, over time, it's as t goes to infinity, apparently, this factor is negative. Okay, so as t goes to infinity, this overall will just go to 0, and t will equal 70. So you know, it doesn't have an exact answer, but you can just make the t big enough, and it'll get closer and closer to 70. So you can sit there and do trial and error. There's no questions like that in the homework where they're asking you to do a guesstimation. But there's that. Okay, so great. Over time, it's going to get closer, and they give you a little chart here. So once it gets out to about 30 minutes, you're going to be pretty much there. Okay, the next type of problem then is the mixture problem. So let's take a look at mixtures. This is section 4. And next problem. So the picture again is basically you have this tank full of some mix, maybe salt water or something like that. You have a pipe going into the tank, and then you have a pipe going out of the tank. Usually when you're going into the tank, they'll give you a value to represent the amount of, like if you're talking about salt water, the amount of salt in the tank, and that'll be in pounds per gallon. And then they also give you a rate of the mix that's going into the tank, which will be in gallons per minute. Then the out rate will be R2 gallons per minute. And then they usually tell you an initial amount of liquid in the tank. So initial amount of mix in tank. They'll tell you how much salt is originally in the tank. Initial amount of salt in tank. And then you can make your differential equation, dA over dt, by taking the difference between the rate of salt in and the rate of salt out. The rate of salt in will be in pounds per minute. And that kind of gives you a hint as to how to set up the structure of that rate. So it's going to be Q1 times R1, because if you look at the units, the gallons will cancel out and you'll just get pounds per minute. Okay? And then minus the rate of salt out, which is usually more complicated. It'll be in pounds per minute as well. But let's say just then in general, the rate of salt in will be Q1 times R1. The rate of salt out is kind of the same thing, except we don't know the amount of salt in there because it's constant. It could potentially always be changing. So it's going to be, we'll say A all over V sub 0 minus R1 minus R2 times T. Okay, so the rate of change of the amount of mix in the tank is just the difference between the input and the output rates of the mixture. And then we have to multiply it by R2. Okay, so you get something like that. Okay. Okay. The initial amount of salt, once you solve this equation, then you would go back and solve for any unknown constants using that initial amount. Okay, so anyways, that's kind of the overview of those. Let's take a look at, I guess, example 5. These problems can be a little bit more in-depth, longer to figure out. Okay, so here we have a large tank that holds 300 gallons of brine solution. And then we have the output valve, or the output pipe, and the input pipe. Okay. Salt entering and leaving the tank. This holds 300 gallons of brine solution. So V sub 0 is 300 gallons. Salt is entering and leaving the tank. A brine solution is being pumped into the tank at a rate of 3 gallons per minute. So that's the R1 value, because you could tell by the units, 3 gallons per minute. We don't really know, I guess, Q sub 1. It's mixed in there, and then the mixture is pumped out at a rate of 3 gallons per minute. Oh, then they tell you the concentration of salt in the inflow is 2 pounds per gallon. So Q1 is 2 pounds per gallon. Okay, and then I think we have enough information to set up our equations. So dA all over dt is going to be Q1 times R1, so 2 times 3 is 6, minus R2, which is 3, times A all over V sub 0, which is 300, minus the difference of the rates. And here the rates R1 and this other rate R2, the rate in and the rate out are the same. So there's no net change of the amount of mixture in the tank. So it basically be minus 0T. So just 3A all over 300 for our rate of salt out. Okay. We could change this thing into a linear equation by moving the 3A over 300 to the other side. I'm going to simplify that into A over 100. So it would be dA over dt plus 3A, sorry, I want to simplify, plus A over 100 equals 6. And then we get an integrating factor. Mu will be e to the integral of A, or sorry, just 1 over 100. 1 over 100 dt. So mu is e to the 1 over 100 t. Multiply through, collapse the left-hand side, so you get the derivative with respect to t of A times e to the 1 over 100 t. And then on the other side, you'll have 6 times e to the 1 over 100 t. Okay. Integrate both sides. Here the derivative and integral cancel, ae to the 1 over 100 t. On the right, there would be a u sub. If you think about it, you know, doing the inverse operation of a derivative, you're dividing by 1 over 100, right? So you'd end up with 600 e to the 1 over 100 t. You could do a u sub if you need to, but you could also do them in your head. Multiply through by e to the negative 1 over 100 t, and you get a equals 600 plus c e to the negative 1 over 100 t. And then we need to solve for c. Okay, so that's where we'll use the initial amount of brine in the tank. So does it even tell us? Recall a large tank held 300 gallons of brine solution. Brine solution is being talked about, blah, 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 the concentrate, blah, 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 leaving the tank, blah, blah, blah. 50, yeah, so there's the initial value. 50 pounds of salt was dissolved initially. What is that? That's A sub 0. So I kind of wrote it, yeah, A sub 0 is the initial amount. We need that. A sub 0 is 50 apparently, 50 pounds. Okay. So we could take that and plop it into this equation that we just got through the integrating factor. So A sub 0 again was 50 pounds. So 50 equals 600 plus c e to the 0 is just 1. So I'd end up with c equaling negative 550. And then I could rewrite my equation. A equals 600 minus 550 e to the negative 1 over 100 t. That's not so bad. 50. How much salt is in the tank after a long time? Well, if you take the limit of this thing as t goes to infinity, the second term is transient, right? So we would have 600 minus 550 e to that negative exponent is going to cause that term to go to 0. This whole thing will go to 0. So over time, you would expect 600 pounds of salt in the tank. Okay. See if that's what they got. Yeah. That wasn't that bad, I guess. Yeah, another example 6. This one looks a bit more annoying. So let's look at example 6. Example 6. Well-stirred solution, example 5, is pumped out of the slower tank at a rate out to, okay, so we're changing this up a little bit. We're keeping some stuff the same, but other stuff is different. Right? So the rate out, so rate, I usually call that R2, is 2 gallons per minute. But everything else is the same, I guess. Let's see what else. So 2 pounds and 3 gallons per minute. So what did I say? Q sub 1 is 2. If I just scroll up on this thing, I can get that previous. Okay, so it's going in at a rate of R1 is 3 gallons per minute, and it's 2 pounds per gallon. And V sub 0 is 300. Okay, so the big difference now is going to be this term here, and the denominator especially. Before, because the rate in and the rate out were the same, there wasn't any variable part in the denominator. But now there's going to be, and that's going to make our life a lot harder. Okay, so example 6. So they changed the rate out. So what's going to happen with our new formula? The first term is the same. It's just 2 times 3 is 6. But the second term is going to be different. So it'll be 2 times A all over V sub 0 is 300 minus 3 minus 2t. And you can think, if you think about it, at every time unit, every minute, there's going to be an extra gallon of water coming, or mixture going into the tank, because only 2 gallons are going out, but 3 gallons are coming in. So when you form your equation, you can see mine's wrong because I went 300 minus, it'll be minus 1. So in my model, it's actually it's the other way around, right? I'm losing one thing per minute. So I need to change it into R2 minus R1. And then it'll be gaining that 1 gallon per minute. So let's see if I get that formula. It's R2 minus R1, I guess. But, you know, whether it's 1 minus 2 or 2 minus 1, you should be able to think about it and just intuitively change it so it works. Okay, so we're gaining 1 gallon per minute. The formula should be plus 1t, right? So anyways, let's go ahead and rewrite it. So I got 2a all over 300 minus t would be, or plus t. It needs to be plus. And so minus 1 plus t. And you can see that's what they got there too. Okay, I'm going to rewrite it now as linear and then solve using an integrating factor. So I'm going to move that second term on the right to the left side. I get plus 2a all over 300 plus t equals 6. And then my integrating factor mu will be e to the integral of 2a, just 2 all over 300 plus t dt. And then this will be e to the 2 ln of 300 plus t. And then I could pull the exponent into the natural log, and you end up with e to the ln of 300 plus t squared. And then you could simplify this into just 300 plus t squared. Okay. Then I'm going to multiply through and collapse the left side, so I get the derivative with respect to t of mu, which is 300 plus t squared, times a. And on the right-hand side, I'll have 300 plus t squared times 6. I want to integrate both sides. On the left here, I just have 300 plus t squared a. On the right, you can do a u sub. You don't need one, though. You'll just get du equals dt with no constants to speak of. And then you just apply the power rule. So 300 plus t cubed all over 3 plus your integration constant. Then you want to divide through everything by 300 plus t squared. So you get a equals 2 times 300 plus t, now to the first power, plus c times 300 plus t to the negative 2 power. Then you could use the initial value to solve for c. So I think they want the same initial value as 50. So a of 0 is 50. So you can plug that in here. You get 50 equals 2 times 300 plus c times 300 to the negative 2. So you got 600. 50 minus 600 is negative 550 equals c times 300 to the negative 2. And then divide by 300 to the negative 2, or multiply by 300 squared, better yet. You get negative 550 times 300 squared. And then plug that back into your equation. You get a equals 2 times 300 plus t plus, or rather minus 500 times 300 squared times 300 plus t to the negative 2. Okay. And I think that's what you should get there. And they're giving me the funny answer in all of its glory. Let's just make sure that's the same thing, right? So if you distributed the 2, you get 600. This thing, if you multiplied that out, would it be the same? Seems like it wouldn't. It's not going to have a 4.95 on it. me see. So yeah, it's basically 500 times not 90,000. So that'd be like, let me just make sure. So 500 times 300 squared is 45. They got 4.95 somehow. Hold on, let me pause the video just to make sure it's right. I could have made a mistake. Oh, I see my mistake. It's 550, not 500. Sorry. It's right there. And this one, and that will make it right. Let me just make sure 550 times 300 squared. Yeah, there we go. Okay. The series circuit problems, there's basically two formulas. You just have to pick which one is required. You can always tell by the picture and kind of how the question is set up. Let's maybe look at the homework problems for those. Let's see if we can't take care of those. Some of these are real nasty, like number 14 is pretty nasty. But anyways, let's look at number 16 and maybe number 18. So number 16, they're telling you 30 volt electromotive force, long story short, that's just your big E of T is 30, is applied to an LR series circuit so that you have inductance and resistance. The inductance is the L, that's given as 0.1 henries, and the resistance is 40, and I of 0 equals 0. So you go back here and you pick the appropriate formula. Okay, so there's two formulas. There's this one, but that's in terms of resistance and capacitance. So we want the other equation. We want that. We want this guy right here. This L di over dt plus Ri. So L is 0.1, and then we have di over dt plus R is 40 times I, and then the 30 is the force that's being. And then we just solve that thing. So you first have to divide by 0.1 to get it into our usual form. 0.1 is the same as 1/10, so you're multiplying everything by 10. So plus 400 I equals 300. Then you could do an integrating factor. So mu is e to the integral of 400, I guess, dt. And that would be e to the 400t. And then multiply through everything by that, collapse the left side, so you get d over dt times e to the 400t times I is equal to 300 e to the 400t. Integrate both sides. Over here, the integral and derivative cancel each other. E to the 400t I equals, do a u sub, you'll get 1 over 400 popping out, so you get 3/4 e to the 400t plus c. Divide everything by e to the 400t and get I equals 3/4 plus c e to the negative 400t. Then if they give you an initial condition, I of 0 is 0, they did. Okay, so I of 0 is 0, so 0 equals 3/4 plus c. Solving for c, you get negative 3/4, so I is equal to 3/4 minus 3/4 e to the negative 400t, and then the second term is transient, so the limit of I as t goes to infinity should just be 3/4, because this thing, e to the negative 400t, if you're to take the limit of that as t goes to infinity, e to the negative 400t is the same as 1 over e to the 400t. So you would get something in the bottom which is going to infinity, and so that would just be 0. Okay. All right. For number 17, then, you have to use the other formula given in the book. So the other formula is this R dq over dt plus 1 over cq equals E of t. And just remind yourself, I wouldn't put this on a test, but I is equal to dq over dt. I wouldn't expect you to be an electrical engineer or electrical engineer. So, you don't have to have Kirchhoff's law memorized or anything. And then where's our book? So I need that formula. Okay, so I got the formula. 100 volt electromotive force, so E of t is 100. The resistance is 400 ohms, so 400 dq over dt. And then they say the capacitance is 10 to the negative 4 farads. So you get Q all over 10 to the negative 4, but that'll just be 10 to the 4th if you take its reciprocal. Okay. Then you got to divide by the 400, dq over dt, plus whatever that is, 10, 1, 2, 3, 4 over 400, q equals 100. 100 over 400, so that'd be 1/4 on the right. Then these guys cancel a little bit. 4 into 100 is 25, so that'd just be 25 q's. So dq over dt plus 25q equals 1/4. Get your integrating factor, so mu will be e to the negative 25t when all said and done. Collapse the left side after multiplying by the integrating factor. You get q e to negative 25t. On the other side, 1/4 e to negative 25t. Integrate. Get q e to negative 25t equals, after you do a u sub, you'd end up with negative 1 over 100 e to negative 25t plus c. Divide out, and you get q equals negative 100, 1/100th, plus c e to the negative 25t. Then use the initial value q of 0 to solve for c. Seems like I did something wrong. I don't know. Let's solve for c anyways. So put 0 over here. Yeah, it's like I got my signs reversed somehow. Well, I see it. That's what I get for skipping steps, right? This would be the integral of 25 dt, so that would be e to the 25t. So this is positive, positive. This will be positive, positive. Then when you integrate, you'll have a factor of 1/25 times 1/4, which is 1 over 100th. And then you'll have positive here, and then q of 0 is 0, so 0 is 1 over 100 plus c e to the negative 25t. And putting in 0 for t, you just get 0 there. So c would end up equaling negative 1 over 100. And so finally, substituting in q is 1 over 100 minus 1 over 100 e to negative 25t. The last one, you gotta use the inductance resistance formula, so you gotta go back to this one. The L di over dt plus 4di, or plus ri. Equals E. And then you'll have 2 that you need to solve. You need to solve the 2 pieces, and I'll let you do that on your own though. Okay. And then you have to hook them up so they have the same value at t equals 40. Okay, so anyways, we'll cut the video there and set you off to do the homework. Some of these problems, like I said, are annoying. You may just want to skip some of them if you can't get them, like number 14. You can always stop by my office hour and I can tell you whether you're on the right track, or even I can kind of give you a hint as to what the answer should be if you get in trouble. But some of them can be a bit, a lot. Okay, I'll just say that some of the questions are a lot of work. Okay, so we'll leave it at that. Thank you for watching as usual, and I'll see you next time.